What a freaking heat wave Europe is going through at the moment. And with this heat wave, I'm inspired with creating a really interesting lesson and experiment. I am going to show you a magic box. This guy is called a Leslie cube, and as you can see, all the surfaces are different. This is a great teaching tool to demonstrate Stefan Boltzmann's radiation law, where power is equal to the emissivity times the Stefan Boltzmann constant, surface area of projection of the material, and the temperature of the body to the power of 4. Now, usually there's an addition to this equation, t to the power 4 of the surrounding environment. The reason is because let's take me. So my body is radiating heat and absorbing the heat of the room. Even if it's not hotter than this room, I'm still absorbing some of the heat. Therefore, there is a power difference between my body and the temperature of the room itself. And that is why there's that little addition to the equation. Enough of that. Let's actually do the experiment. For this, I'm going to need to boil a kettle in this weather. So I have a little foam surface here just so that it doesn't conduct too much heat and I can move it. Pour the scalding water in very carefully. The experiment does work better in colder temperatures. Now you don't actually need that much hot water. I'm going to stick a thermometer in. It's just above 85 degrees Celsius, not too hot. So what I'm going to do is I'm going to use a thermal laser gun. I'm going to point it at the center of the surface, 72.5 we'll say. Now the temperature can vary a good bit, so you should repeat this experiment several times. Now let's measure a black shiny surface, 71.5, a white shiny surface, 71.8, and a copper surface, only 40.6, 40.5, 40.4. It's dropping. The temperature is decreasing over time, so it makes sense. But the copper surface was significantly lower, while the black shiny surface was clearly the highest temperature reading. What is actually going on? You might ask, what's the point of the Leslie cube? So it's really interesting to show that unique emissivity value that every surface has. Depending on the color and depending on the material and the type of surface it is, some surfaces radiate heat better than others. In this case, you can conclude that the matte black surface was the best radiator of heat, while the worst one was copper. Copper, however, is a great conductor of heat. So remember, there are 3 different forms that heat can transfer: conduction, convection, and radiation. Radiation is usually the third type. Black matte surfaces are so close to being defined as a black body, something that absorbs and radiates heat at an exceptional efficiency. In fact, 100%. So the black body emissivity value is 1. Something that is a terrible black body and doesn't absorb or emit at all, perfect insulator you might say, has a value of 0. And that is the problem with these thermal guns. If you look into the coding or into the description of their manuals, a lot of these guys already assume an emissivity value of the thing that they're targeting. In this case, I looked it up that it was 0.9 assumption. In fact, this is my tricorder that I'm building. I'm almost done building the case for it. But this guy also has an infrared sensor, and it too assumes a emissivity value of 0.9 on the things that it's targeting. Now that we've covered the theory and the experiments, let's actually do some mathematics. Let's actually calculate the power rating of that black matte surface. So this is the equation for the Stefan Boltzmann equation. Let's calculate the power of that black matte surface. We need a few values. First of all, we're going to assume the asymmetry value of 0.9. Technically, that black matte surface could have been better, but like I pointed out, that thermal gun already assumed this. There's a few errors in my statement, but for argument's sake, let's say 0.9. And it has no unit because it's a relative term. Next thing is the Stefan Boltzmann constant. That's just a number. I have it there. 5.67 by 10 to the minus 8. The surface area needs to be in meters squared. It was 10 centimeters by 10 centimeters, 0.1 by 0.1. T is the temperature of the body, but it needs to be in Kelvin. We need to use absolute when we have an actual T value. This is a rule of thumb for you. If you have an equation with an absolute temperature value, you need to use Kelvin. If it's a delta T value, you can use Kelvin or Celsius. The room temperature is 26 degrees Celsius. It is freaking hot in here. 299.15. Now, with all of this pointed out, we can actually sub everything into our equation. Whoopsie daisies, I did not clean the board. When we sub in all the numbers, just need to be careful in your calculator so you don't make too much of a mistake. Roughly 3.2. So the power emitted via radiation is 3.2 watts. Hope you found that educational and useful. I am now going to go turn on the air conditioner before I die. Stay safe in the heat waves.